Hello everyone, and welcome to Module 2. We are done with the thermodynamic chapters, and now we move to the subject of waves. There are two chapters that cover the subject of wave, chapter 16 and 17. We will spend 2 weeks covering chapter 16 and 1 week covering chapter 17. Waves, as I am sure most of you have studied waves, there are two types of waves. One is called transverse wave, and the other one is called longitudinal wave. Did I spell it right? The longitudinal wave. Okay. A transverse wave is a typical wave that you see, for example, ocean wave. So it looks something like that. And a longitudinal wave is a wave that looks something like that. And so on. Okay. In the transverse wave, the direction of motion is this way. And as you can see, the amplitude of the wave is here. The height of the wave, that is like that. So this is the amplitude, the height. As you can see here, the velocity is perpendicular to the amplitude. For a longitudinal wave, the motion is the same. Let's say the motion of the wave is like that, but the amplitude here is this way. Okay, it's along the direction of propagation, okay, where in this case the velocity is parallel or anti-parallel to the amplitude, okay? So that's the amplitude of the wave. One way to think about wave is that the wave moves, but the particles are there. For example, let's say you're looking at an ocean wave. The wave rides the water, but the water doesn't move. You see what I'm saying? For example, if you hear that there is a wave, the wave that is, let's say you are on the beach and you have your feet extended into the water and the waves are hitting your feet. Well, where does this wave come from? Well, it came from very, very far away, say maybe 1,000 miles away. It's been traveling for a couple of days until it hit your feet. Of course, the water is not moving with it, okay? So the wave is riding the water. In other words, the water here is the medium, and the wave moves through it. You get that? So it is when we say the motion of the wave or the speed of the wave, we're talking about the wave itself, the motion of the wave that is riding the medium, or going through the medium rather, okay? But it's not the motion of the medium, okay? All right. So wave speed here, so let me just say V here is the speed of the ripples, if you will, that move across the water. An example of that, let's say I have a rock and I throw it into the water, okay? So what you will see, you'll see ripples moving through, and so the water is not moving, it is the wave that is moving. You get that? Okay. Now we can measure the speed of the wave, for example, on a string, on a stretched string. If you have a stretched string, say for example a string of a guitar. Here is a guitar. I can draw a guitar, something like that, right? Then let's say I have one string here along, okay? And of course the string is stretched. If I would pluck the guitar, say here, okay? So what's going to happen? A wave is going to move in this direction, and another wave is going to move in this direction. They're going to reflect, but that's the subject of chapter 17. But if I am interested in finding the speed of the wave as it goes from here, for the moment I plucked it right here, and which is the source of the wave, and then all the way to here, okay, for example. So to measure that, there is a formula that we're not going to derive. It says that the velocity of the wave on a string is equal to the square root of the tension in the string divided by mu. Mu here is called the linear density. linear density. And it's basically mu is the mass of the string divided by its length. So let's say this is the string of the guitar. Here it is. Okay, that's the string of the guitar before I put it into the guitar. If I measure its mass and I get some number, and I measure its length and I get some length for it, the mu value here is basically mass over length. Okay, simple. That's the meaning of it. Okay, let me give an example of this. And this example comes from the book. Example, where am I? Hold on. I think example 1, sorry. There it is. Oh, I have the book here. It's second page, so should be able to get it here. Oh, one more. Here is the formula right there. So the velocity of a wave on a string is equal to the square root of the tension of the string divided by the linear density. Okay. Here is an example. Look at the diagram right there. It says a 2-meter long metal wire is attached to a motion sensor. Maybe the motion sensor is right here. Okay. And stretched horizontally to a pulley 1.5 meters away. Okay, there's the pulley, and the length of the string here is 1.5 meters away. Then connected to a 2 kilogram hanging mass right there. Okay, that provides tension. So the mass is pulling, because of the weight, and so there is a tension in the string here. A mechanical pick plucks a horizontal segment of the wire right at the pulley, creating a small wave pulse that travels along the wire. The plucking motion starts a timer that is stopped by the motion sensor when the pulse reaches the end of the wire. What is the wire's linear density? He wants mu. If the pulse takes 80 milliseconds to travel along the wire. Okay, let's talk about that. So what I have in here, let me 16.1. So what I have in here is something like that. Here is say a wall, here's the table, and then I have here is the pulley, and here's the string right here, and it's vibrating, the string is vibrating, and then here you have on the other side, you get a mass, M equals 2 kilogram, okay? The length of the string here is 1.5 meters, and the velocity is going in some direction, let's say this way. I think the book will put it in that direction. It doesn't matter which direction. And I want to know the velocity. I'm sorry, you want to know what is mu, what mu is. He says that if it takes the wave to travel from here to here, okay, or the other way around, whatever, the time is, what is it? Wait, 18 milliseconds, okay? So it takes 18 milliseconds to travel, the length of that, okay? He wants mu. Well, we know that velocity is equal to the square root of the tension divided by mu. So I can find an expression for mu here. So that will be v squared equals t over mu. And therefore, mu is equal to t over v squared. There it is, okay? So in this case, I need to know what is the tension and what is the velocity, correct? To do that, well, let me get the tension first. The tension is caused by the weight of the block, this block right here, right? So I can just use Newtonian law. Of course, everything is in a static situation in equilibrium. So here is the mass, here is the weight, here is the tension. So the tension is equal to mg. So that makes it 2 times 9.8, and that will be, what is it, 19.6 Newton. So there we go, I got the tension. Okay, so I got that. Now we'll get the velocity. Well, what the velocity is equal to? We're not assuming any acceleration or anything. So the velocity, basically distance over time, which is the length of the string divided by the time. The length, of course, we're not concerned with. He said it is 2 meter length. See that? 2 meter. But we're only concerned with the length where the wave is moving. So the wave is moving from here to here. The wave is not moving after it passes it's not after the pulley right here. It's only here. And this distance is only 1.5. So in this case, the length of the string is 1.5 divided by the time is, what is it, 18? 18 milliseconds. So that makes it what? 0.018. Is that right? And then we calculate that. Here's my calculator. So I have 1.5 divided by 0.018. Answer 83.3. So I get 83.3 meter per second. Okay, there it is. So I got the velocity. That's it. It becomes pretty simple. So mu is equal to t over v squared. So that will be 19.6 divided by 83.3 squared. And that will give me I get 2.82 times 10 to the power of negative 3 kilogram per meter. I forgot to mention, because mu is mass over length, so the unit in this case kilogram per meter, right? And there we go. You get that simple problem. Okay, good. The next thing is we want to talk about the wave equation, or the displacement formula that describes the motion of the wave. First, we talk about, in your book, I'm talking here in section 16.3, sinusoidal wave. When we say sinusoidal wave, we mean the word sinusoidal comes from the word sine, okay? So it means a wave that can be described with a sine function. That's one aspect of it, okay? So it can be described by sine or cosine, really. Some books you'll find it in cosine. But it can be described by a trig function, either sine or cosine. That's one thing. The second thing is that a sinusoidal wave is a periodic wave. It means it repeats itself over and over, exactly the same way. So it doesn't change, okay? This is important. So it does not change. It repeats itself over and over and over again. And the period is always a constant. In other words, the time it takes it to make one cycle is exactly the time it takes to make the next cycle and the next cycle and so on, okay? So here the period is constant, the frequency is constant, it's repetitive, cyclical, keeps repeating itself, okay? And on top of that, it can be described by a sine wave. So these are special kind of waves, okay? Most waves out there are not really sinusoidal. Maybe they are close to being sinusoidal, but they're not exactly sinusoidal waves, okay? A perfect example of sinusoidal wave is the SHM. The simple harmonic motion. Simple harmonic. This is not our subject, but basically something like, imagine you have a pendulum, for example. Here's a pendulum. And let's say I give it a little push, and then the pendulum is oscillating. Let's say it's oscillating between those 2 points right here. So it's oscillating to and fro, where the angle here is really small, say 1 degree or 2 degrees or something, okay? You could hardly see the oscillation, okay? In this case, we say that this is SHM, okay? So SHM is always a very, very small amplitude, very small displacement, okay? I mean, there's more to it than that, but that's not our subject. But these kind of waves are sinusoidal waves, okay? It just oscillates, and we're assuming a perfect pendulum in a perfect world where it doesn't attenuate, it doesn't stop eventually, you know what I mean, like a grandfather clock or something. So it's always oscillating at that same amplitude, same period, and so on, okay? Anyway, so when we say sinusoidal, like I said, it can be described by a sine function. Of course, it looks like a regular transverse wave. Let me make a drawing of it. Drawing really slowly, so I don't want to mess it up. And let's assume it looks something like that. again, we want to have the same amplitude, a little bit longer, and so on. Sorry for the lousy drawing, but it looks something like that, okay? And of course, this, we call that the amplitude of the wave, A, okay? The amplitude, so we have the amplitude. A, okay? And then we have the distance between the two crests or two troughs, okay? Whichever. We call that the wavelength, lambda. Okay, lambda, which is the wavelength. It's in meters. Of course, the amplitude also measures in meters or centimeters, whatever unit you use. And the lambda is also that. Now, the time it takes to complete one lambda. So, for example, let's say I have a timer. The time it takes for this point to go to this point, from crest to crest or trough to trough, or any point really from here to here, whatever. Okay, the time it takes it to complete one cycle. Okay, it's called a period. So time it takes to make one cycle. Just like imagine a pendulum. The time it takes the pendulum to make one full swing is called a period. Okay, and I like to use the term, the symbol tau. Your book uses big T. I'm going to use tau. We'll reserve big T for temperature, but it's okay. We'll call it tau. Okay. Also, we have something called the frequency. Now, the frequency is the number of cycles per unit time, specifically per second. So, number of cycles per second. Okay. In other words, how many cycles have the wave made in 1 second or a period of time? So that's the symbol F. Okay, and the unit of it is hertz. Okay, the unit of cycle, of course, is second. Right. The unit of the unit of period is the second. Okay. Then we have so if I have the length of the wave is lambda. Okay. If the length of the wave is lambda, and it takes time tau to make that one lambda, so therefore the speed of the wave as it moves, v here, is basically lambda over tau. Make sense? Okay, so we have, this is the first formula. Now, we also know that since the frequency is the number of cycles per second, and the period is the time it takes to complete one cycle, we also have the frequency is the reciprocal of the period, okay? Or the period is the reciprocal of the frequency. So with those two, I can say that the velocity, it's lambda over tau or lambda f. See that? These are very important equations for this chapter as we start the solving problem later. Okay? So these are the equations. There are more to that, more later. But for now, let's just move on to the next topic, and that is the mathematics of sinusoidal waves, the mathematics involved. The wave, or the function that describes the wave, really, it starts from what is called the wave equation. What I'm about to tell you is beyond the scope of the book, so this is not something that is part of our course. So you have something called the wave equation, okay? And the wave equation is a partial differential equation. I don't know if you have taken a course in that. I mean, I'm sure you, I mean, you probably have taken a course in ordinary, some of you, ordinary differential equation. But for the wave equation is a partial differential equation that looks something like that. Partial squared psi partial x squared equals 1 over v squared partial squared psi partial t squared. Again, this is beyond the scope of our course, so if you want to skip it, that's fine. But basically, this is called the wave equation. And this psi function describes the state of the wave, the motion of the wave, the displacement of the wave. It gives a lot of information about the nature of that wave. And this is just a one-dimensional wave in terms of x, where psi here is a function of x and t. That's why it's called partial differential equation, PDE, is because the derivative here with respect to time and with respect to space. Okay, it's more than one variable. Okay, and then so you solve this equation. Oh, and then this coefficient here basically gives you information about the speed of the wave. So here v is the speed of the wave. Okay, and when you solve this equation, this is a PDE, like I said, partial differential equation. When you solve this equation, you come up with the function psi that describe the motion of that equation, and it looks something like that. Again, this is not in our book. Something like psi naught sine kx minus omega t. Okay, that's the equation. In other words, if you take this and plug it into the wave equation here, it will satisfy it. Okay, they'll be equal. In other words, if you take this and you plug it on the left-hand side and the right-hand, they'll should be equal to each other. Okay, but where psi naught here is the amplitude of the wave, and k is the wave number, and omega is the angular frequency. Okay, but our book immediately begins with an equation that's similar to that without going through all of that. Okay, so anyway, so let's go back to our course. But I'm telling you this just to show you where the displacement function or the wave equation this came from. It came from this partial differential equation here. So our book, let me go back to my notes. It looks something like that. Let's start with at t equals 0. Okay, the wave equation looks something like that. D, which is replaces psi. Okay, the Greek letter psi. So the book uses capital D. D of x and t at 0. Okay, is equal to a sine, and then you have 2 pi x over lambda plus phi naught. Okay, now if you ask where did this come from, again, it came from the solution to this equation, and this is not covered in our book. You got that? Okay, so a here, like I said, this is the amplitude. As a matter of fact, every time you look at a wave equation, the coefficient of the sine or cosine is always the amplitude, no matter how complicated it is. If it's just on that side, on the left side of the sine, that's basically the amplitude, the height of the wave, you know. Okay, and then of course lambda is the wavelength. That's the wavelength. And then this phi naught is called the phase constant. Okay, I'm going to come back to it in a minute. For now, just accept it for now. Okay, of course the x here describe the displacement, or displacement in the x direction. Okay, all right. I want to write it in a different way. Okay, here is how it works. So we said that the velocity is equal to lambda f above, right? And we also said it's equal to lambda over tau. We define the angular frequency omega, okay, to be equal to 2 pi f. Or we can say it is 2 pi over tau. Okay? What's the unit of that? Well, the pi is radian, and this is tau is second, so the unit of it is radian per second. I'm sure you've seen that in mechanics, of course. Okay? Then we have something called a wave number, k, and it's defined as 2 pi over lambda, okay? And a unit of it is radian per meter, right? Lambda is the unit of it is meters, so it's radian per meter. So now if I go back to my expression for the velocity, this one, I have v equals lambda f. Well, if lambda, k equals 2 pi over lambda, so lambda is equal to 2 pi over k, correct? And so I can put it here, so that will be 2 pi over k times f. Well, what is f? F is equal to, here, use this one here, f is equal to omega over 2 pi, right? So I can put it here. So that's going to be omega over 2 pi. The 2 pi's cancel out, right? So I end up with omega over k. Another way of saying it is that omega is equal to vk. Okay? So now, if I go back to the wave equation, the one I've just written right here, okay, it will look something like that. I'll leave it as an exercise for you to show it to show you to yourself that this is actually true. Kx minus omega t plus phi naught. Okay? So what's the meaning of this one? Okay. The meaning of it is this. So this is, like I said, the k is the wave number. We define it to be called the wave number. Omega is the angular frequency. Now you have a minus sign here. As a matter of fact, it's usually plus or minus. The minus, it means wave moves to the right, not the left, the right. And if it's plus, wave moves to the left. Okay? So if you have a wave moving in the positive x direction, you put a minus there. If it's moving in the negative x direction, you put a plus. Got it? Okay. That's one thing. Now, you also have the initial condition. In other words, at t equals 0, for example, okay? How did the wave, or let's say at t equals 0 and x equals 0, how did the wave look like? Okay, what, or the value of the wave? Well, let's test it. Go back to this formula right here. We're just going to keep it minus for now, okay? The default, just wave moving to the right, okay? So look at that. So if I go d of 0, 0, so that's going to give me a sine 0 minus 0 plus phi naught, all right? And so this tells me that d of 0, 0 is equal to a sine phi naught, okay? So what is phi naught in this case? It is a function or a value that describes the initial condition of the wave. So it describes the initial condition of the wave. More on it when we do examples. Okay? All right. Yeah, let's do an example right now. I want to do an example from the book. I'll do at least one example from the homework, one problem from the homework. Let me do example 16.3. Let me find it in my hard copy first. Okay, just the next page. All right, let's see if I can find it quickly. One more. that the one? Oh, 63 I'm doing. One more page. Sinusoidal, yeah, it should be under sinusoidal waves. Here is the V equals lambda F, the one I just talked about. There it is, that the one? Yeah, okay. Oh, this is, no, not that. Sorry. Here's the final version of the wave, right? The one I just showed you here. The minus sign indicates going to in the positive x direction. There we go. Okay, here we go. It says, just put it on the side. It says a sinusoidal wave, which means it's a wave that can be described with this formula right here. Okay. He said a sinusoidal wave with an amplitude of 1 centimeter. So we have a wave with an amplitude A of 1 centimeter. And a frequency of 100 hertz. So I have a frequency of 100 hertz. Travels at 200 meters per second in the positive x direction. Okay, so the velocity of the wave is 200 meters per second and in the positive x direction, which means it's going to be a minus, right? Kx minus omega t. Okay, and then he says at t equals 0, the point x equal 1 meter is on a crest of the wave. Okay, now why did he mention that? I'll tell you in a second why. At t equals 0, he says the point x equals 1 meter is on the crest of the wave. Whenever he gives you, or it's not just this problem, any problem that you may read in any subject, engineering or physics or mathematics, when he gives you an information about the beginning of the dynamical system, so at t equals 0, so and so was happening, or t equals 1, so and so was happening, what he's giving you really is giving you a boundary condition. Okay, what is a boundary condition? You know, when you take, for example, go back to calculus 1. Let's say you are integrating, say, x dx, right? And when you integrate it, as you know, it is 1/2 x squared plus c, right? Your math teacher told you, here is the answer, and that's it. You box it and you're done. That's it. But in engineering or physics, well, you got to do one more step. What is that? What is c? You see what I'm saying? C is very important. I mean, in math, it's not important what C is. But if you're doing some, application, like in physics or chemistry or engineering, well, you need to come up with the exact value of that answer. So you need to find C. Well, how do you find C? Well, you look into what's called the initial condition. At t equals 0, what was the system doing? Something, say x equals 3. Well, you plug it in here to find the value of C. This is called initial condition because t is 0. Boundary condition would be something like on the 3rd second, the system was something, okay? And then you use this information to find C and so on, okay? The same thing applies for differential equations and partial differential equations. You find, you end up with C1, C2, several constants of integration, okay? And you need to find those values. Well, here it is. This is basically what it is. He said, at t equals 0, the point x equal 1 is on the crest of the wave. So he's giving you this hint. Why does he give you this one? Because he wants you to find something that is unknown. I'll come back to it in a sec. Okay? So this is basically what the problem is given to us. Then he said, determine the values a, v, lambda, k, f, omega, and t, and phi naught for this wave. So we're going to do all of that. And then he said, write the equation of the wave, and then graph it. Okay, and then he said, draw the equation. Okay, let's do it. So let's find them one by one. So we know that lambda is equal to V over F, right? And I have both of them. V is 200. Frequency is 100. So it's just, what is that, 2 meters per second. I'm sorry, lambda, 2 meters, sorry. So it's just 2 meters, right? Okay. And then we have K, the wave number, which is 2 pi over lambda. So that will be 2 pi over 2, and that will be equal to pi over 3.14, okay? And then the next one is omega. Omega is what? 2 pi f. F is given to me, 100 and 2 pi, so that's going to be 200 pi. Let's leave it like that, okay? The next one is tau, the period, and it's the reciprocal of the frequency. The frequency is 100, so that's 1 over 100, and that will be equal to 0.01 second, okay? Or we can say 10 millisecond, okay? And then what else? And then we have phi naught. I think we got all of them. A, V, did we get V? A? Oh, A is given to us right here. He said sinusoidal wave with amplitude 1 centimeter. We said find A. Well, we give that to us right there. Okay. And then V, lambda, K, F, omega, T, all of that is given to us. Great. And then the last one we need to find is phi naught. Again, what is phi naught? Remember I told you it is the phase constant. I know you still don't know what is it. That's okay. Bear with me. Okay. How do we find it? We find the phase constant with the boundary, with the initial condition. This one. Okay. This is where this comes in handy. Basically, the phase constant tells you what was the wave doing in the beginning, initially at t equals 0. What was the wave what was the state of the wave, if you will? Okay. How do we find it? Simple. Let me go back. So after we've gotten all of that, I want to go back and write the wave equation. The wave equation basically is d of xt, this is the general expression for the sinusoidal wave, is equal to a sine kx minus omega t plus phi naught, right? There it is. Now, for our case, I want to apply the initial condition. So here is how. He says, what does he say? He says, at t equals 0, the point x equal 1 is at the crest of the wave. This is important to picture. So in other words, at x equals 1, here's the wave. I'm not going to draw the whole thing. That will be for part C. So at t equals 0, here is the crest of the wave. Something like that, somewhere. This is x equal, this is x-axis. This is 1. It's at the crest of the wave, right here, at t equals 0. Here, at t equals 0, the point x equals 1, which is right here, the crest of the wave was right there, okay? The crest of the wave wasn't at 1.5 or 2, no, it was right here. The crest, I mean, that's other waves here, and so on, but that's basically what he's saying, all right? Let me plug this information here. So I have here d for 1, 0 is equal to a sine. Now it's a sinusoidal wave. All these are constant. K and omega are always the same. Remember, I'm trying to find phi naught. Okay, I'm trying to find this one. So K I have already gotten is pi. So that's pi x, and x is what? 1. Minus omega, which is 200 pi, times what? 0, right? Plus phi naught. There we go. So, now what is this value? Remember, d is this way. I forgot to mention this. The d, this is the function d right here. Right here, okay? So basically the wave moves up and down like that, d, okay? This is x. So he says at 1, 0, which is right here, So D is equal to what? What would that be equal to? Well, that would be equal to the amplitude, isn't it? Because that's the height of the wave. He said crest, even the point, when he said the word crest, immediately that's the height of the wave at A. So that means this is really just A. So in other words, A equals A sine pi plus phi naught. See what I'm saying? I can plug in the value of A already. He gives it to me, 1 centimeter. But it doesn't matter because they're going to cancel out anyway. So those two cancel out. So I end up with 1 equals sine pi plus phi naught. Of course, sine what gives me pi? Gives me 1. That means it's equal to, let me put it properly, pi plus phi naught equals sine inverse of 1. So that will be pi over 2, correct? So phi is pi over 2 minus pi. That's minus pi over 2. So phi naught is equal to minus pi over 2. That's how you find the phase constant. Okay? So now I'm ready. I'm done. I'm ready to write. This is part B. Sorry, that I think it says it. Okay. So therefore, he said find the function of the wave. So d of xt is equal to, A is equal to what? 1 centimeter. I'm just going to make it 0.1 meter sine kx, which is, again, k is equal to right there, and omega is right there. So k is pi, omega is 200 pi. So we have here pi x minus 200, what is it? 200 pi t, I'm sorry, 200 pi t, 200 pi, yes, 200 pi t minus pi over 2, okay? And there we go. That will be the last form, the last expression. Let me see how we did it. There we go. He has it right there. Oh, he actually put the numbers. So there we go. So we have here, oops. So let me use my mouse. It's probably better. So d of x is 1 centimeter, which is, I converted it to meters, sine, and then you have pi x, there it is. He loves unit. He put the unit there. Minus 200 pi, which is 628 t, minus pi over 2. You got it, guys? Okay. The last step, now with this, what I want to do, I want to look at this one, and I'll make a graph of it. Well, how do I do that? So let's draw it. This is part C. So we know that at x equals 1 meter, we have a crest at also t equals 0, right? So if I make a graph of it, I'm going to draw it, and you tell me, or you think about how I did it. It looks something like that. Let me just start it. I have 1, 2, 3, 4. Let's make it 5. 5 is here. 1, 2, 3, 4, 5. Right there. I'm going to be oscillating between the two. It's going to be something like this. Let's do one more, maybe one more, before my hand gets tired. There we go. Okay, there we go. So this is d of x, d. This is x in meter. This is d. Let's make it in centimeter. You can change the unit if you want to. This is the amplitude. So this is the amplitude. A equals 1 centimeter. This is 0, okay? And this is at t equals 0 as well. This is x equals 1. This is 2, 3, 4, 5, and 6, and so on. Okay, and then this is at t equals 0. Okay, at t equals 0, x equals to 1, and then the wave is moving with velocity equal to 200 meter per second, I think. Okay, and the wavelength, which is basically the distance between the two crests, or two troughs or two crests, whatever, and that would be equal to 2 meters, and there we go. That would be one shape of the wave. Okay, everybody got that? Okay. Let me jump to the homework. Maybe I'll do one more problem. I'm trying to remember which one I wanted to do. There are three homework problems that are related to those. Number 46, 45, 46, and 50 something, and 57. Okay, I'm not going to do all of them. You go ahead and try 2 of them, and I'll do just one. Let's see. Let me pick number. I'll pick number 45. Okay. Let me go to the book. By the way, I want to thank those of you who sent me some help, some hints on how to operate those the Note 1 and how to. I had difficulty magnifying, and I got an email from Jason. Thank you. How to let me try it now. He said that if you push, I'm a Mac user. I'm not familiar with the PC, but he said if you push Control plus, it should magnify it. Let me try it. It's not bad, I guess. On the Mac is much more visible than that. But anyway, that's cool. Thank you. And one hint that I got from Kevin Poe, P-U, sorry if I pronounced it wrong. He said you can convert Note into PDF, and I like this idea. I can export those notes into PDF, and I can just include them as part of the course as a transcript for the video. But I haven't figured out that yet. When I look up a YouTube video on how to do that, the way their OneNote looks like is different from mine. So if you know how to do it, let me know with that. I can't find anywhere where I can find. See, if I push home here, there is no file or anything. I'm looking for something like export or something like that. I can't find it here. But anyway, let me go back to the problem. We're going to do number 45. There it is. Okay, so 45. Okay, this one. So we are looking at this figure. Let me magnify it. Okay, there it is. Oh, cool. It only magnifies that. I thought it would magnify everything, which I don't want. Okay, good. Anyway, there we go. So we have a graph. It says, whoops, sorry, not this one. 45, there we go. What is the graph? Oh, this one here. Okay, I got it. So this is the statement, and this is the graph. It says figure 45 right there is a history graph at x equals 0 of a wave traveling in the positive x direction. So it's going in this direction, okay? What is the wavelength? Well, that's easy. We can just measure the distance between two crests or two troughs, right? What is the phase constant? Okay, so we're going to find phi naught. Again, you find it by applying boundary condition or initial condition. And then he said write a displacement equation, which is basically the wave equation of that. Okay, let's do that. So maybe I should draw that. Okay, the graph looks something. This is number 45. the graph looks something like that. I'm going to copy it from my notes. Sorry, it's, whoops, where did this go? Oh, that, let me just, doesn't look pretty. And then the graph looks something like this. 1, 2, 3, 4, 5, 6, right there. And it looks something like that. Sorry, bear with me. I know this being slow like this is kind of boring watching me. Anyway, they get 0.4, this 0.3, 0.2, 0.1, and this is the time axis, okay? And this is d, the displacement function right there, in millimeter, okay? That's what is given in the problem. And of course, from here to here is the lambda. We can also say it's also the period, right, in terms of time. The wavelength and the period, right? And that's it. Okay, so now we go back to the problem. He says, what's the wavelength? Well, we can just read it from just by looking at it. So the wavelength would be something like from 0.2. Remember, this is in time. So from 0.2, the period. Let's get the period first, okay? The period will be from 0.2, which is this trough, to this trough, correct? So that's from 0.2 to 0.4. So it's 0.4 minus 0.2. That's 0.2 second. All right? That's the period. Now, the lambda here is not terribly obvious because we're not given the x-axis in terms of displacement. We're just given in terms of time. Okay, but there is a trick to it, of course. Lambda is equal to v over f, correct? Or, if you will, v tau, right? And now, if you look up the velocity, is it given to us? Yes, there it is right there. I thought it was. Here, it says the wave traveling in the positive x direction at 4 meters per second. So we are given the velocity. So here the velocity is 4 meters per second, and therefore lambda is equal to v tau. So that will be 4 times 0.2, and that will be 0.8 meters. There we go. So lambda is 0.8 meters. Okay. Oh, there! Look at that. Oh, with I'm using my hand. You can actually magnify it with my. I didn't know that. It's just an accident, by sheer accident. That's cool. Okay, there we go. Now we come to part B. He said, what is the phase constant? Okay. So what is the phase constant? Phi. How do we do that? Well, remember, the phase constant is it describes the initial state of the function. So basically, if I start, here is my initial, the displacement function, dxt is equal to let me just write it down, sine kx minus omega t plus phi naught. Remember, I put minus here because he says it's moving in the positive x direction. So now, d of 0, 0, so that will be a sine 0 minus 0 plus phi naught, right? Okay. Now let's look at the graph. So this is important. Let's look at the graph. Here is the graph that we have right there. What is the value of the amplitude? Well, the amplitude is right there. All right? And that's equal to, if you look at the graph, it's 2 right there, right? 2 millimeter. Okay. So I know that. Okay, that's one thing. Now, what is the displacement at t equals 0? Well, here's the time, right? The t equals 0 is right here. This is the displacement. This is the displacement function. The function is right there, which is what? Minus 2. You see what I'm saying? So the amplitude is 2 millimeter, but the displacement, which is d, is minus 2 millimeter. Make sense? Okay. So now I go back and plug it, all that stuff in there. So here, d of 0, 0 is minus 2. You can convert it to meters, that's fine, but they're going to cancel with that. So that's minus 2 millimeter equals positive 2 millimeter sine phi naught. So that gives me sine phi naught is equal to minus 1. And this immediately gives me, so therefore, phi naught is minus pi over 2. Got it? So that's the initial displacement of it. So now when I go back and write the displacement function, so it's going to look something like this. Let me just write it down. So a sine kx minus omega t plus phi naught. So that will be equal to 2 millimeter, okay? Leave it in millimeter if you want to. Sine, and then we have here k. Do we have k? Oh, I need to find k. Sorry, I forgot to mention that. So k, which is what? 2 pi over lambda. So that's 2 pi over, we already got lambda to be equal to, right there, 0.8. If you do the algebra here, k will be 5 pi over 2. Okay? And then omega, which is 2 pi over tau, and that will give me 10 pi. Work it out. You'll find out this is correct. So anyway, so we have that. So in this case, I will have so we have kx, which is 5 pi over 2x minus 10 pi t minus pi over 2. Okay? And there we go. This is the displacement function. Write the displacement equation. It's a constant value and so on. Okay? Let me tell you what's the meaning of this phase constant. I keep forgetting to mention that. Let's say I'm going to explain it to you in an example. Let's say I have a pendulum. Here's a pendulum, and this pendulum is oscillating. So let's say I make you walk into a room, all right, and then you walk in and you see the pendulum is oscillating to and fro like that. You see it in front of you, it's oscillating. Okay, so the pendulum at some point, I tell you, at some point, say 5 minutes ago, the pendulum was not oscillating. Then I put it into oscillation. Okay? Now, well, how did it start? It's possible. Let's say I have the pendulum which is at rest. It's right here. So it's just sitting there happy. Okay? So one way to do it, I would just kick the pendulum or push the pendulum, give it a little push like that, and then it start going into oscillation. Right? The other possibility, there's a million possibilities, but that's not, well, it's one possibility. The other possibility is that I would literally hold the pendulum and hold it like that with that angle, and then I'll let go, and now it is oscillating. Both oscillations after, say, some few seconds are identical. There is no difference between them, especially if they are the same angular amplitude. They're identical. But both of them, the way they started is different. Here, start with that the pendulum, initially theta is 0, you know, the angle here, and then I give it a push, and now it's oscillating. This one, however, at t equals 0, it has an angle, some value, and then I'll let go. You see what I'm saying? That's the phase constant. So this theta naught is the phase constant. In other words, how did the oscillator started? How did the pendulum start? Well, with this case, it started with some phi naught equal to, pick a number, 10 degrees. Here, the phase constant started with 0 because it was right there, sitting there. Then I give it a push or a kick, and then it starts oscillating. So in the beginning, the phase constant is 0. Okay, so basically that's what the phase constant. It tells you how did the oscillating system started. When at t equals 0, what was the the state of the, how did it start? You got it? Okay. We have already done an hour. I was going to cover Doppler effect, but I think I want to always keep my videos to be around an hour. So I'm just going to stop here. And in the next lecture, the video lecture, I'm going to be covering the remaining 2 topics. And that will be Doppler effect and sound waves. I think you'll find sound waves very interesting. Okay, those are the 2 topics that I'm going to cover. I'll try to cover them or publish those videos around the end of the week. I mean, I still have other videos I have to create for the other classes that I'm teaching. So anyway, if not, I will do it over the next weekend. So by next Monday, you'll find those videos available to you. Okay? So, and that's it for the time being. So have a good week. Bye-bye.